Hey guys, so welcome back to part 2 of the Learning ROS through Simulation tutorial workshop series. So last Saturday we had done part 1. The video is now posted to the link there on YouTube. These are all the steps that we looked at. And in addition, I had added a couple more steps that we hadn't looked at in terms of looking at all the other worlds. Today we're doing part 2. So we're going to look at how to create a map using the TurtleBot default SLAM libraries. And then we are going to use that map to drive the TurtleBot autonomously. And then hopefully we will see if my virtual machine can handle it, but hopefully we will be able to look at the camera feed from the TurtleBot and essentially this last step, using our map autonomously to drive wherever we want. We will play it by ear. I don't know if we will get to that step today, only because our map specifically is kind of proprietary. So we will see when we get there what we want to do. So if we open up Ubuntu again, so last time we had exported the environment variable TurtleBot3 model equals burger. Essentially, let me just write it out here in the terminal. More specifically, we put that in our bash RC file. This TurtleBot3 model needs to be set. This is a variable, an environment variable, and that needs to be set before we can run any of the TurtleBot3 scripts. So that's why the command export sets the variable to the latest whatever you set it to. So in this case, if I hit enter, and then we can type in env to list all of our environment variables. Which echo just spits out whatever you tell it. In this case, we're telling it to look up the variable with the $, and then the name of the variable, which is TurtleBot3 model. As we can see, it's set to burger. If we do, for instance, if we set this to one of the other models, such as the Waffle _pi, and we run that again, we can see it got updated to Waffle Pi. Why I bring that up is because I figured out that the burger model does not have a camera on it. So we're actually going to be wanting to use the Waffle Pi today in today's tutorials. So what you can do is if we go in to our home directory, and then you can say show hidden files. And then in our bash or .bash rc file, last time we added to the bottom this export TurtleBot3 model burger. I'm just going to change it right here so I don't have to retype it every single time in every terminal instance, to set it to Waffle instead. Waffle Pi, that is. There's a Waffle, without the pi, just TurtleBot3 model Waffle. That is a discontinued version, as far as I can tell. It should also work, but I haven't tested it. So we can save that and then close it. And then for it to immediately take effect, we can run the command source space .bash rc. And there we go. So now if we list out the TurtleBot3 model again, it's still Waffle Pie. If we go into a new tab and we also just copy it. There we go. Now we can see that it's defaulting to Waffle Pie. So now that we have that, the next step, the next thing we're going to look into is mapping. So before we can autonomously drive anywhere, this goes for autonomous cars, this goes for any sort of autonomous vehicles, including drones and whatnot. Before we can tell the robot to drive somewhere on its own, we first have to let it know what the environment looks like or should look like. So, of course, the more detailed these maps are, the, I guess, easier it will be, and more accurately, your robot will be able to drive to wherever you tell it to drive. So to create a map, that is called mapping. TurtleBot has a bunch of scripts, programs already set up to handle all of this. Today, we're going to be using the SLAM package gmapping, which ships with TurtleBot3. We installed it in the last tutorial. I think it was part of that long list of packages that we installed. So let's go ahead. I'm going to clear that just so it looks cleaner. And we will start mapping. So the first command is going to be ROS launch TurtleBot3 Gazebo, TurtleBot3 world.launch. That is the command we were looking at last time that just loads the world. And then once again, if you're using a VM, or even if you're on an actual machine, I had mentioned last time, there's the GZ physics command that we're going to run to speed up the physics engine. So once Gazebo loads in a new tab, we're going to run the following command, GZ physics, and then this value, the 0.01, that's the value you'll have to play with individually, depending on your computer. I figured out that for my laptop, with everything running and Zoom running and everything, that should be a decent value to get the real-time factor up to about 1.0 real-time speed. We will see. I actually may need to increase it a little bit since Zoom is also running. And I'll just show this to you guys. So you can even go faster than real time. So if you go some crazy high value, you can see the TurtleBot actually is freaking out and jumping around, but look, we're hitting 10 times speed, 15 times speed. So I don't know why you would ever want to go that fast, but you can. So that's out there. We are going to restart everything because maybe I flipped the robot upside down. I don't know. Shouldn't have been putting it to 10 times speed. So the Gazebo tab, I've noticed Gazebo doesn't actually exit until you go to the tab and hit Control-C to kill the program. And then from there, we're just going to relaunch these things. So we're going to launch the Gazebo launch file first. And then once that loads up, we're going to set the physics step size so it isn't super laggy. And then from there, we are going to eventually run the TurtleBot3 SLAM. Let's run the step size now that it's up. Now we can run the TurtleBot3 SLAM launch file using the SLAM method gmapping. I think for our actual rover, we're probably either going to use the nav stack, the navigation stack package, or potentially Cartographer, which is Google's implementation of a SLAM library. But the G mapping is already all set up for this tutorial. We set it up last time, and it defaults with TurtleBot. So we will continue to use that for this workshop. And then we're also going to run, see, already looking much better. We're going to run the teleop node so we can actually drive it around. And right now it's just rolling around. I don't know why, but since I haven't given it a velocity yet, but as you can see, as it rolls and computes more of the map, it gets more data from the point cloud. It starts filling in with either white, or light gray, to signify that there's no obstacles there. Black, so for all of the walls, we can see black represents an obstacle that it can't cross. And then this, right now it's transparent, but if we actually save it to an image file, it will be some shade of gray in between the white and the black. And that will represent that it hasn't been there and it doesn't know yet what obstacles may be there. So now we can drive around. I'm going to back up a little bit since looks like we ran into this post right here. So I'm just using X to do that. And then I'm going to hit S to stop, A to turn counterclockwise a little bit so we don't hit the post again, and then W to drive forward. And as you can see, I'm actually just holding down the button, the W in this case. Every time you press it, it just increases these values by, looks like I think 0.01 for the linear velocity and 0.1 for the angular velocity. This is why using a joystick is a little bit easier, because you're not having to go click, 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 click on your keyboard to, update these small values. We're just going to continue driving around here, gaining more knowledge of the map, because how LiDAR works is it's a laser that we're shooting out and computing the distance between our sensor and whatever object the laser bounces off of. So in this case, we can see that, say around this post, the second post in the 9 dots, we hadn't been able to see, and we still can't see. You can see there's no green dots kind of on this back wall. That's because the post is in the way. So kind of like for, if you're, I guess, taking a picture or even just looking, and there's a wall, you can't see behind the wall, right? So you can't get any data, you can't infer as to if there's an object behind the wall. So we're just going to continue driving around until we have all of the, I guess, all the objects, obstacles, walls, all outlined in black. So that should be about good. As you can see, what's interesting is it actually just skipped a little bit, and all these dots, our point cloud isn't lining up exactly correct anymore. I think that's because my computer lagged or something, and we must have missed a odometry step. So it thinks that we were, based on where our, how far our wheels drove, it thought we were at a different position than we actually were. But now it jumped back to the correct position. What I was going to point out is we don't have a full map yet. You can see there's still certain areas on a couple of them that haven't been computed. We don't have the full black outline. That's okay. I'm not going to waste the time in driving over there. If you had the time, it would be better to do that. But as we're going to see in just a second, we'll be able to compute that real time when we're driving autonomously. So what's really cool about this is once we have a map, it's not set in stone necessarily. We will still be using the LiDAR and all of our sensors in real time to compute if there's a new object that may enter the map or an old object that we didn't detect before. And so our path planning algorithms will be able to identify the object and drive around it safely so it doesn't collide. So what we're actually going to do is we are done here, and we actually want to, I guess, reset everything, refresh. But before we close out absolutely everything, I forgot we haven't saved the map yet. That would be nice, right? So before you exit the SLAM package, we need to save our map, which we're going to use the map saver to do, the map saver package. So we're going to run this command. Which is ROS run map saver -f for, I believe that's to actually tell it what file you want, and then the location of where we want to put the map. So we're going to create a map called map with no file extension. And we're just going to put it straight in our home directory. You can change that if you want, but notice we're going to be running, we're going to be looking that up later. So actually, I take it back. It writes two files. We're creating a file called map.pgm and map.yaml. So the map.pgm is that grayscale image I was referring to earlier, I think before the meeting started. It's a grayscale image with actually exactly what's represented in our viz right now. So the white being, no obstacles, black being obstacles, meaning you can't pass them. And then some gray value in between to represent that we don't know if it's an obstacle or not. So now that we have written our map, we have created our map, I'm just going to continue to exit out here of the SLAM package and also of the teleop node. So we are completely, and don't forget to exit all the way out of Gazebo as well in the command line. There we go. Now we should be completely dead, if you will, nothing running in the background. Kind of signifying a new session, right? A new day or something. Say we want to come back to this later. So now we're going to do the autonomous navigation using the SLAM map that we just created. SLAM stands for simultaneous localization and mapping, by the way. So what that means is at the same time as we're localizing, which refers to finding our position, I guess, in the environment, determining our position in the environment. In this case, based on our map, we are also mapping. So we're constantly updating that map. And like I said earlier, if a new obstacle comes into the map, we'll be able to detect it. So that's what SLAM is. Hopefully you can see why it's useful for something like autonomous cars or rovers or any other robotic systems. Say a human enters the environment, you don't want to say drive over the human. We don't want any accidents. So next up, we are going to relaunch the Gazebo node, the TurtleBot3 world.launch. And again, every time we're going to update our physics step size. There's probably a way to do this, actually, to hard code it in Gazebo so you don't have to do this every single time, but I haven't found that out yet, so I won't share knowledge that I don't have with you. And then we're going to run this command. Give it a second. I'm being a little bit slow. ROS launch TurtleBot3 navigation. So this is the actual navigation library to perform real-time SLAM and autonomous navigation. This will load up RViz, which is the visualization tool that we looked at. We created the map in. And from there, we have to do two things. We have to first tell it approximately where we think it is, so it can align the map that we had created with the current sensor readings. And hopefully it will be able to intelligently match all those point clouds, all those points. And so it will localize ourselves. And then after we do that, we will be able to give it different waypoints to follow, different target positions to eventually end up in. And when we do that, it will autonomously drive there. Or if you give it a target goal to drive to that is, say, behind a wall that it can't get to, then it will say, hey, I can't get there. It's not possible. So the first thing we're going to do is this 2D pose estimate. It thinks we are kind of, I guess if we're counting left to right, going across the rows. So there's, I guess, pillar number, column, this dot number 1, 2, 3, 4, 5, 6. We're kind of between 2 and 4 right now is where it thinks we're at. But as you can see on our map, we're actually at the bottom of the 9th little cylindrical cylinder here. So what we're going to do is we're going to click on 2D pose estimate. And this will allow us to draw an arrow. And we're going to draw it roughly. We're going to click roughly where it is at and drag in the direction that our robot's heading. And then release. And that should align the map. So we are about here. So I'm going to click, hold, drag. We're at about a 45-degree angle, and then release. And as you can see, the two maps jumped on top of each other, and we are now localized. So now what we can do is click on 2D nav goal. And say we want to drive kind of behind the first pillar. We can go to our map, and this is our first pillar. We can draw an arrow. Maybe we want to head in that direction. We want to end up in that direction, that heading, and it will autonomously go there. So as you can see, it's backing up. It's telling us all the new plans. So it's actually detecting, hey, it doesn't think it has space to go through there. So it's recalculating. And that's what each of these, all these output statements are telling us. If you can see, let me see if I can try zooming in here. It's a little bit laggy. There's a fine yellow little arc right coming out of the front of the rover, the robot. That is our local plan. which is basically the plan. It's trying to get the motors such that the robot is always following the global plan, which is this red or blue path right here. So it's essentially always trying to make sure that we're always following the path and not getting off path by, say, having one side of the motors drive too fast. So we break it up into that local and global scope, if you will. And as you can see, we're in the simulation, we're turning the corner just as we thought we were. And this is actually a little tricky because the Waffle model is actually a bit bigger, bit larger than the burger model. So it's having a little bit of a tough time trying to figure out how to give it enough space to drive and give it clearance to drive through that little passageway. We'll see if it figures it out. It should. You can see the map is also jumping around a little bit because, like I said, it will re-update the map for any new obstacles it may find. And with that being said, all new data points, regardless if they were old obstacles or new obstacles, will be considered the new, latest and greatest obstacles. So it will slightly start updating our map as we go along. But unless we actually save that map back into that, using map saver into our home directory like we did, our old map will always retain the original information. So yeah, as we can see, it got there, and actually it's still a little bit confused as to how to align itself correctly. So I'm going to tell it to go where it has a little bit more space. And then hopefully then it'll get there in the right orientation and then be happy. So there we go. We can see in our output goal reached. So it's telling us it successfully made it there where we told it to go and in the orientation. Cool. So next up is looking at the cameras, getting camera feeds. So this would be a good time to talk about topics because I don't think we've done that yet. I'm going to just clear this terminal window so it's a bit cleaner. And so we're going to talk about topics. So topics are how data is, I guess, how the stream of data works. So everything in ROS, pretty much everything in ROS revolves around the flow of data from one program to another. And that's how we can have all of these programs arranged in a graph, with every program being its own node in a graph. If you don't know what graphs are and whatnot in software, don't worry. Especially if you haven't taken a data structures class, you probably haven't heard of what a graph is. But essentially, we're creating all these programs, and they're all running at the same time, as you can tell by all the tabs. And they're all interacting with each other through a flow of data. And how that works is we can either publish data, so we can create new data and try to send it off somewhere for it to be, used by some other program. That is called publishing data. Or we could subscribe to data. So that is looking at where it thinks data should be updated and stored at. And whenever there's a new update of that data, it will grab it and take it in and be able to perform some functionality based on it. So we can look at our ROS topics by typing ROS topic space and then list. And there we go. These are all the different data flows that are being produced and things are reading from. So it's quite a bit, actually. Waffle, the Waffle model does a lot. So these AMCL are for navigation. Then we have all the data for the camera. This camera RGB image raw is the actual every frame coming off of the camera. So that's what we're going to look at in just a second. We're going to look at the raw camera feed. We have stuff for Gazebo. We have an IMU, which is an inertial measurement unit. It's a type of sensor that tells you your orientation. We have our map. So the map that we created is actually being fed in to our navigation node using that data stream. And then, yeah, I think this move base, that's all for navigation. We can see all the, like I mentioned earlier, the local and global cost maps. So that's for the local planning and the global planning of path planning, trying to figure out, what's the shortest path from A to B. That's how we dragged the arrow and it was able to compute the path. That was indeed the shortest path, according to its algorithm that it's running. I think it's running Dijkstra's by default, Dijkstra's algorithm. Just a couple more. This scan right here, that's our LiDAR point cloud data scan. All those green dots are represented in a data structure contained in scan. And yeah, so what we're going to do is, now that we know that it is actually publishing the camera data to this camera RGB image raw, we are going to go to another program. Hopefully you have it installed, called RQT, which stands for ROS QT. It is a graphical user interface, I guess, creator, if you will. It allows you to easily set up a graphical user interface, a GUI, using the Qt framework. So we'll let this load up and in. There we go. It comes up. I think this is because I had a couple different packages that needed to be installed that aren't installed. You shouldn't have any errors, but hopefully RQT has popped up. We're going to go to plugins and then visualization and this image view. As you can see, it is very, very laggy right now because of all the data that we're trying to simulate, all the sensors and whatnot. So there is actually a good chance that my entire virtual machine is going to crash here. So we will hope that it doesn't, but if that does, I will have to load back into it. In the dropdown, we can click on camera RGB image raw. That's the topic that we're looking at. We're wanting to view from. There we go. So that is the camera feed. It should be real time. Although it looks like everything is crashing. So yeah, probably not a great idea to run Zoom and Chrome and everything at the same time as trying to run, SLAM, some super intensive processing in a virtual machine. So that's one way to view the camera stream. There are other ways, and I'll put them in the written tutorial on how to actually, access the camera stream in a slightly different way, in a way that you can actually save the image, the actual a frame of the camera stream that's coming in. And also in the future, if once we're actually writing code for controlling the simulation, the TurtleBot will be able to capture those frames actually with code and save them or use them in computer vision. So that is to come in the next tutorials.